time, I want to say we went through most of the notes. We were almost about done. I know we talked about acids. I want to say we were on like slide 7 or 8. We were strengths of bases. Yes, we talked about that. Talked about the pH scale. Okay, so this was kind of today's. So I'm going to pause here. Let's go into the slideshow. All right, so this was today's do now, ladies and gentlemen. Oh, no, it wasn't. The universal indicator was today's do now. So today, ladies and gentlemen, we started off by talking about what is a better indicator. And again, if we're talking about our acids and base, what we're really talking about is the concentration of hydrogen or hydronium ions or OH ions, right? So there's the H. If it's an acid, we have a very, very high concentration of hydrogen ions, and the lower my pH gets, the more acidic I become, the fewer OH ions have. And then, of course, the opposite is true for bases. Again, we had talked about this slide, just another way of thinking about it. And this is a log scale, 0 and then 10 to the negative 14. Don't worry about that. That's just some math. Again, the further away from 7 that you are going to get, the stronger the substance becomes. So if I'm down here in the 0, 1, 2, 2.5, 3 area, then those are strong acids. If I'm in the 6, 5, 4, 3, 3.5 area, then those are weaker acids. Again, further from 7, the higher towards 12, 13, 14 I get, those are going to be strong bases. 8, 9, 10, 11-ish, I guess, are going to be the weaker ones. So when we measure acidity, this is the one that has to do with today's do now. We can use litmus paper. We can use a universal indicator. And there are a bunch of different ways of measuring pH. As a general rule, litmus paper, yes, will tell you if something is an acid or a base, but you're not going to get an actual pH range. It'll just say, yes, it's an acid. No, it is a base. Okay, that is what litmus paper does. If you want to get a much more closer, or if you want to get a much more accurate pH scale reading, then what you're going to need is a universal indicator. So down here, purple cabbage, believe it or not, is a universal indicator. You can see all these different colors that you can get from purple cabbage, and then each of these colors represents a different pH. Litmus paper either is blue, it's a base, it is red, it's an acid. But it won't tell you strong, weak. It doesn't tell you any of that. It doesn't tell you anything about pH. It just tells you if it's an acid or a base. So going back to today's do now, ladies and gentlemen, the more accurate pH is going to always be with a universal indicator, like a cabbage juice or a red cabbage. Okay, so there's that information for you. All right, so again, litmus paper, it only turns red, it will only turn blue. Some litmus paper can give, oh my God, there's like a fly in my room and it's driving me crazy. But it only indicates acid or base. It does not indicate pH. Neutralization reactions. I'm pretty sure this is where we left off last time. So an acid and a base together will yield what we call salt and water. Remember, the whole idea behind an acid is that in an acid, what we have are extra hydrogen ions. Okay? So when those hydrogen ions are extra, they sort of, what's it called? They're sort of floating around. There's more of them, right? However, in a base, we have extra, what are they called? Hydroxide ions. And those hydroxide ions, of course, are OH. Well, if you think about your basic chemistry of water, if I have a hydrogen and I add it to another grouping of hydrogen and oxygen together, then I would have two hydrogens and one oxygen, or I would have H2O. So if I take an acid and a base and I mix them together, then I am going to get salt and water. This is a neutralization reaction. A neutralization reaction will always result in a pH of 7. All right. So, strong acids can neutralize strong bases. Weak acids can neutralize weak bases. However, do not, if you were to mix like a strong acid with a weak base, then you normally have like what we call a buffering reaction, which is where you're not going to see a huge change in the pH. All right. So, again, and you saw this buffering reaction, I want to say, in your virtual lab. Again, if you add strong acid, strong base together, neutralizes. Weak acid, weak base together, they neutralize. But if, as a general rule, if you have, if you're mixing a strong acid or base with a weak acid or base, you're going to end up with what we call a buffering reaction, which is where you will not see a huge change in your pH. All right. So where were this? Exactly. Yep. Okay, so this was number 16 in the note catcher. We had number 17 in the note catcher as well. Awesome. All right. So neutralization. So antacids, right? So like, let's say you get an upset stomach and you're not feeling so great. Antacids, Tums, right? They're basically a weak base. When they go into your stomach, you chew them up, you swallow them. What it does is it's going to create a slightly weaker acid, and therefore you end up feeling better. But it doesn't totally neutralize it, right? This is a buffering reaction. Again, buffering is when you're just going to change the pH, but not by a huge amount. True neutralization results in a pH of 7. Buffering neutralization means that you're just going to slightly change your pH. By the way, buffering, super important to maintaining homeostasis. All right, so now we are going to take a look at our 9 true-false questions at the end of your note catcher. All right, so here we go. Excuse me. Number 1, true or false? Acids dissociate, that means they basically come apart in water to form hydronium. So that would be H3O negative ions. Do acids give off hydronium ions? True or false? Give you a few moments to fill that in. Alrighty. Second question. Come on. There you go. So, acids dissociate. This is actually wrong. Okay, my answer was wrong, but whatever. They actually form H3O positive ions, so that's interesting. All right, number 2, acids taste bitter, and bases taste sour. True or false? Acids taste bitter, and bases taste sour. True or false? All right, so acids taste bitter and bases taste sour. This is false. Acids are sour. Acids, think of like orange juice, lemon juice, lime juice. These are all acids. They have that like sour taste. Bases, I mean, I don't really know why you would be eating bases, but whatever. But if something very popular to do back when I was a kid, if a kid cussed, they'd wash their mouth out with soap. Trust me when I say soap, which is a base, is very bitter tasting. All right. So there's that. Number 3. True or false? A strong acid is a strong electrolyte. True or false? A strong acid is a strong electrolyte. True. This is electrolyte means it helps to conduct electrons or electricities. This is why we have things called battery acid because acids can conduct electricity. Very strong acids can conduct electricity very, very well, which is why we use them when we make batteries. Which also kind of brings me to back to like an environmental issue. Never just throw away your batteries; they need to be disposed of properly. All right, true or false? Ammonia, pH 10, is a stronger base than an antacid, pH 8. True or false? All right, this is true. Remember, the further away from 7 that you get, the stronger the acid, the stronger the base. pH 10, the number 10, is further away from 7 than 8 is. Okay? It's like 3 steps away versus 1 step away from 7. Think of a number line. So that is a true statement. True or false? The pH scale measures values from 0 to 14, with 7 being neutral. Number 5, true or false? The pH scale measures value from 0 to 14, with 7 being neutral. All right, this, of course, is a true statement. pH scale measures values from 0 to 14, and halfway through that scale is 7. 7, therefore, is neutral. Anything under 7, we know is an acid. Anything, 8 or above, we know is a base. But 7 is the midway point, therefore 7 is neutral. Like pure water, H2O, neutral. True or false? pH stands for the power of hydroxide. All right, let's see. This is false. pH stands for power of hydrogen or hydrogen power. And again, it comes from the French because some French scientists figured this out. And he's the one that named it. I don't know why now it's like a tiny p and a giant H. Hey, that's whatever, but that's what it stands for. The power of hydrogen, not hydroxide. Power of hydrogen, pH. Number 7, bases produce hydroxide ions in aqueous solutions. Aqueous solutions are just basically like liquids. Oh, bases produce hydroxide ions in aqueous solution, and this is true. In fact, it is the measure of these hydroxide ions. The more hydroxide ions we have, the stronger the bases. The fewer hydroxide ions we have, the weaker the bases. All right, second to last one. True or false? Liquid pH indicators are always going to give exact pH values. Liquid pH indicators are always going to be exact in their pH values. True or false? And this is false. Most liquid pH indicators are going to give you an approximate pH value. If you want to get an exact pH value, then you are going to have to use a pH meter, which is similar to what we used in our virtual lab. Okay, we actually have those here in the chemistry department for the science department. Where literally it's almost, if you think of it like almost like a thermometer, right? Where you what's it called? You can put the meter into the liquid and then it'll give you an exact value. But usually, if we're using a liquid indicator, we're gonna get an approximate value, not an exact one. All right, last one. True or false? Adding acids and bases together always results in a neutral solution. If I add an acid and a base together, it is always going to result in a neutral solution. True or false? And this is false. Remember, a strong acid and a strong base will become neutral. A weak acid and a weak base will become neutral. But if I mixed a strong acid and a weak base, I get what we call a buffering reaction, which doesn't allow for a huge change in pH. It'll slightly lower the acid number, but it won't, I'm sorry, I should say it will raise the pH for an acid because that'll actually make it weaker. So it'll make it slightly weaker, but it will not 100% neutralize it. So we have neutralization reactions always between strong acids, strong bases, weak acid, weak bases. But if I mix one that's weak with one that's strong, I get what we call a buffering reaction. And by the way, buffering, super important to maintaining homeostasis. So, for example, your blood, I want to say, is just slightly acidic. I always forget if it's slightly acidic or slightly basic. I'm pretty sure it's slightly acidic. And there's a reason for that. It's a so that way if there's for whatever reason there's like a large amount of something that enters your body because it's that kind of weak sort of substance, it is going to be able to buffer and maintain homeostasis. If we recall, homeostasis is one of our characteristics of all living things. And if you do not maintain homeostasis, of course, that can be fatal to many organisms. Okay? Again, adding bases together acids and bases together can produce a neutral solution, but only if they are equivalent strengths and amounts. If they're not equivalent strengths and they're not in the same amounts, then you will have what we call a buffering reaction, where yes, you will have a change in pH, but not a very dramatic change in pH.